Hello and welcome in. This is our first video, our first chapter in Chemistry 202. This is Organic Chemistry, a quick 1-week overview of organic chemistry, which of course is a enormous topic, which you could devote many semesters towards. But we will take just a few classes, just a week here, to give a quick introduction to organic chemistry, thinking about ways in which we can represent our organic molecules, looking at a few different classes of organic molecules, including their properties, some nomenclature rules, and some typical reactions. So, with that being said, let's jump into it. We can start here thinking about, well, what is organic chemistry? Originally, the idea was looking at molecules that can produce living organisms, but our definition today is now based on carbon-based compounds. The reason being, well, these quote-unquote organic compounds don't have to come from living organisms. We can synthesize them in the lab as well. Carbon here can form many different compounds because of its unique chemistry. It likes to form 4 stable bonds, and so we can build large branching extended structures with very wide ranges of properties. In organic chemistry, we're looking at carbons, hydrogens, nitrogens, and oxygens, with special guest appearance by a few other elements, but predominantly just these 4 elements. Even still, with just these 4 elements, we can have an enormous range of molecules, an enormous number of molecules, all with very different properties. So we'll be looking at those this week, thinking about these different molecules. Again, trying to look at the properties of these molecules, some of the nomenclature rules, and some reactions. If we want to represent our organic molecules, well, we can go back to our Lewis structures. We remember these from previous classes, I'm sure, representing each atom as its chemical symbol, and lines to represent our bonds. Sometimes we also include those extra dots to represent lone pair electrons. And there we go. We can represent every single electron, well, every single valence electron in all of our atoms. A lot of organic chemistry is being, I like to say, efficient, but other people might say lazy. We can try to give the same information by doing less. So below there we have our condensed formula, which has all that same information if we know what we're looking at, but we don't have to draw the extended structure. We can just say, okay, maybe CH3, this group at the end, shows up so much that we can just represent it that way. Here, this CH3 at the end, let's do a little circling here. This CH3 at the end, this is a common motif, a common pattern, and so maybe we just write CH3, and this is giving the organic chemist that same information. Likewise, if we have some carbons connected to 2 other things, maybe we can write that as CH2. And again, same information, just written in a more condensed way. And then lastly here in our molecule, we have an OH group. Well, this OH group shows up enough. We can just abbreviate OH. Don't need to include the lone pairs, don't need to include the bonds. This is conveying the same information. We know that this means the same thing. And we'll start to look at these functional groups, these common patterns, in more detail in our next video. But there we go. That's our sneak preview. Trying to condense these common patterns into, well, simpler ways to represent them. In fact, we also have line formulas, which is taking this idea even further. Instead of even writing our atoms and our, well, abbreviated versions of these groups, we can have every carbon represented by the end of a line or a bend in our line. Hydrogens we can omit. When we're looking at these line formulas, we get to assume that there are enough hydrogens to complete our octets. Lone pairs can be written here, are often omitted as well. So again, this means the same thing. We can have, well, this end of our line represents a carbon. Carbons have to have 4 bonds, so there have to be 3 hydrogens here that are just not being shown yet. This bend in the line also represents a carbon. There are 2 bonds on this carbon. Carbon has to have the octet. It has to have 4 total bonds. So there are 2 hydrogens that we have efficiently left off. And so, okay, this line formula, this is what we understand it to mean. But we can just draw this simple quick line to represent that same exact molecule. So just a quick review here, Lewis structures. We love our Lewis structures from General Chemistry 1. Here we're showing all the bonds and all the lone pairs. The connectivity of our atoms looks great. For our condensed formulas, well, we're being more efficient. Some of these patterns show up all the time. We can start to just abbreviate those patterns. And we'll get some practice here on learning what these different groups mean and seeing them all. Like I said, look forward to that in our next video. If we go even further than that, our line formulas, well, the carbon atoms are drawn as pieces of our line. Our hydrogens are omitted if they're attached to carbons, and we just get to understand that there are enough hydrogens to complete those octets. What's nice here about our line formulas, they do a better job of conveying 3-dimensional shapes. If we have this carbon here, this is a carbon that is sp3 hybridized. That carbon should have a geometry that is, well, everything 109.5 degrees apart, tetrahedral geometry. Our Lewis structure probably doesn't show it as tetrahedral, but our line structure, well, it does. It does a better job here. All right, if you'd like to pause, we have a practice problem. Let's see if you can take a moment, get the right answer here. All right, perfect. Hopefully we got, on this left molecule, we have 6 carbons and 6 hydrogens. And on our second molecule, let's see, 1, 2, 3, 4, 5 carbons. Each of these carbons has to have has to have an octet. We can see why we like to abbreviate. It starts to get a little bit messy. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like perhaps 10 hydrogens. Double check if my counting is wrong. It sometimes is. But it looks like that's what we have. Our second problem, again, if you want to take a moment and pause, feel free. All right, what are we doing here? We have a chlorine. We have CH2, CH2, CH, OCH3, CH3. My goodness. Okay, so this chlorine is going to be a chlorine atom. Our CH2 is going to be a carbon with 2 hydrogens on it, which means, all right, we're going to need to connect to 2 other things. We'll just go in order here. I'll assume the chlorine is attached to that carbon. Then we have another CH2. CH2 is going to be another kind of bridging carbon connected to 2 hydrogens, but also 2 other things. Then we have CH. CH is going to need 3 more bonds. Well, we have 1 bond to that hydrogen, we have 1 bond to the rest of our molecule from before. And now we have two more. One is going to go out to this OCH3 group. One is going to go out to this other CH3 group. So we can have OCH3. And we can have CH3 here as well. And we'll connect these all with little lines. Does this look okay? All of our carbons do have 4 bonds. Even if they're a little bit messy, it does look like we have 4 bonds. Apologies for my drawings. Our hydrogens have 1 bond. This chlorine, if we want to complete this diagram, we can include all the lone pairs. Same thing with this oxygen. We can complete our lone pairs, complete that octet. This looks like our nice molecule. And so there we go, a quick crash course in how to draw some organic molecules, and hopefully we'll get enough practice. We can start to recognize these organic molecules as well. All right, moving on. We do want to look at a few different classes of organic compounds. We want to try to think about, okay, what types of properties do we expect from these molecules? Can we give some names to these molecules? And like I said, let's think about some typical reactions that might occur. So with even just a handful of elements, we can build a wide variety of molecules, which are useful in organic life forms. We're useful in carbon-based life forms. Things like proteins, hormones, carbohydrates, all the things that build up cells in biology are these organic compounds. As well as other useful molecules, where we have listed plastics, soaps, perfumes, all these useful molecules built mainly out of carbon with a handful of other elements. We're going to start here with our simplest class of organic compounds. These are known as hydrocarbons. Forget about every other element. We're just looking at hydrogen and carbon. This is our quote-unquote simple organic molecules, but they're still can be incredibly complex, and we can still have a wide variety. If you think about it, our carbons, they do get to connect to 4 other things, up to 4 other things. We can have long chains. We can start to form rings and loops. We can start to form wide branches. We can have different types of bonds. Carbon can form double bonds or triple bonds, even just with other carbons. And so even just hydrogen and carbon, we can have many compounds available. So just 20 carbons, 42 hydrogens, okay, 366,000 compounds available. These are known as, of course, isomers. The same chemical formula, but with different structures, different properties. Okay, hydrocarbons are going to be our most simple organic molecules. Let's even narrow it down further. Let's just look at alkanes. Alkanes are a type of hydrocarbon that contain only single bond. These are known as saturated. We have the maximum amount of hydrogens on these carbons, filling up those carbons with hydrogens so that we don't have any double bonds. This is saturated in the same sense that fats can be saturated or fats can be unsaturated. Saturated fats will have all of those carbons as, single bonded, filled up with hydrogens, which, makes them a little bit worse for you in terms of nutrition because they can pack together, stack on top of each other more efficiently. All right, if we're thinking about our alkanes, these get to be sp3 hybridized, right? All single bonded carbons all have the same hybridization. If we're looking at alkanes, they do have a similar or a formula for their chemical formula. For every n carbons that we have, we need to have 2n plus 2 hydrogens. Right? Each carbon has 2 hydrogens attached to it, and then 2 other carbons, probably. and then, okay, plus 2 extra hydrogens here to cap our ends. Right, so each of our carbons has a top and a bottom, and then the 2 at the end have 1 extra hydrogen. 2n plus 2. We can start to see some names here. Methane is our smallest alkane, ethane, propane, right? We can start to build out these chains. At a certain point, we can start branching or starting to form rings, all these kind of things, right? But these are the alkanes. If we're thinking about the properties of our alkanes, sp3 hybridization, carbon and hydrogen, we do not get to have hydrogen bonding. We're going to have non-polar molecules. The properties are going to be dictated by London dispersion forces. And so we can start to see the size of our molecule will start to influence its melting point, its boiling point, and its phase. Right? All these properties are dictated by those intermolecular forces, in this case, solely by London dispersion forces. We also have the number of isomers available, even just up to 11 carbons in our molecule. We can have 60,000 different isomers. Yeah, can get very complex pretty quickly. All right, there we go. That's our simplest type of molecule. We do want to look at what to call these molecules. We want to look at our nomenclature rules. Our rules here, we're going to have a prefix to tell the number of carbons in our longest chain. We're going to have the ending of our molecule tell us the type of bonding, whether we have single bonds or eventually double bonds or triple bonds, or perhaps other types of functional groups. And then if we have branches, if we have other things attached to our organic molecule, we want to indicate those also at the beginning of our molecule's name. Right? So that is our general idea. We're going to have, okay, the ending will tell us kind of the bonding, single bonds or double bonds or triple bonds. We can have the prefix tell us the number of carbons in the chain, and then before that we can list any groups that are attached to our longest carbon chain. So these are the kind of 3 pieces of the name of our molecule. For the ending, for our alkanes, our ending is always going to be ane, alkane. So whatever ane means that there are only single bonds. For the number of carbons in our longest chain, we have, here's the list up at the top right. Meth, eth, prop, bute, pent, hex, hept, oct, none, dec. We do need to memorize these. We do need to be comfortable using these prefixes. We'll try to get enough examples so that that memorization process becomes easier, but there it is. We'll start to look at how we can list our groups in just a moment, but maybe we have some halogens attached to our carbon chain. Maybe we have some branches on our carbon chain. All right, so here's our process. In order to name our alkane, we need to look for the longest chain in our molecule, the longest string of carbons. This is not always starting at the top left and ending at the top right. It's not always, going left to right. Maybe our molecule is twisted around upside down. Maybe it's confusing. We need to be a little bit clever. We need to be rigorous here in searching for what is the longest continuous chain of carbons. We have some tiebreakers here. We'll start to get some practice with this in a bit. If there's a tie, we want to choose the chain which contains the most alkyl substituents, which contains the most branches on it. And once we identify that longest chain, we need to number it. In order to tell where the groups are attached to our chain, we need to know what is the beginning and what is the end. So if we have a chain of carbons with groups stuck to it, try to number those carbons, one at the beginning, the highest number at the end, where our groups are attached to the lowest number carbon possible. And then, okay, we want to identify what groups are attached to our chain and where are they. We have a couple of different types of groups. We can have electronegative substituents, right? Something like a halogen, chlorine or fluorine or bromine. Just change it to an O ending, and that is our halogen attached to the carbon chain. Chlorine becomes chloro. Fluorine becomes fluoro. If we have alkyl substituents are going to be something like a CH3 attached to our carbon chain, or a CH2, CH3 attached to our carbon chain. We can name these branches again using our prefixes from the previous slide. So scrolling back here, we have meth, eth, prop, right? This table up at the top right. If we have a branch instead of the main chain, just add YL to the end of this name. So a CH3 group attached to our carbon chain would be methyl, meth YL. Our CH2, CH3 below that would be F with that YL ending. So this could be an ethyl group. Right, so we can list out these substituents, list out these groups, and say where they are attached to our carbon chain. We have an example up in the top here. We can try to, okay, first step, identify the longest carbon chain. We can try to start somewhere. Here's one carbon, here's two carbons. We can go, okay, 3 carbons in a row. Is there a way to have 3 carbons in a row somewhere else? Is there a way to get 4 carbons in a row? We can try going down like this. Still just 3 in a row. Okay, so it doesn't matter. We have 3 carbons in a row. That dictates the name of our molecule. This is going to be prop. Meth, eth, prop. Prop means 3. Everything is a single bond, so our ending has to be propane. 3 carbons, all single bonds. Well, there is something else attached to our chain as well. We also have this group. This is a branch, and it looks like a CH3 group attached to our chain. We can try to number this chain. 1 carbon, 2 carbons, 3 carbons. Or if we want, we can have the other way. 1 at the bottom, 2, and then 3 over here. Either is fine here because the branch for this molecule always lies on that second carbon. If our numbering system led to our branches, our groups, lying on different carbons, then we need to be a little bit more careful. We want to number the carbons to have the groups on the lowest numbers. In this case, okay, we have that second carbon has a methyl group. So we can write that in the beginning. There's a methyl on that second carbon. We call this molecule 2-methylpropane. This 2 refers to where that methyl is. We separate our numbers and our words with a hyphen. There is no space between any of this other stuff. Methylpropane is all just one word without any spaces. And oh, look at that. We got the answer correct. All right, this might seem like a lot so far, and you're right, it is a lot so far. But let's give a little practice here. So let's see if we can pause the video, take a moment, see if we can name the molecule written for question A, see if we can draw that molecule for question B. All right, hopefully we had some success here. Let's go through it. We need to first look for our longest carbon chain. If we want, we can have 1 carbon, 2 carbons, 3 carbons in a row at the top. That is pretty good. Let's see if we can do better. 1 carbon, 2 carbon, 3 carbons, 4 carbons is a little bit better. Can we do even better than that? 1, 2, 3, 4 carbons like this as well. Which is the right way to do it? Well, we want to do it in the way that leads to our groups on our smallest numbers. And if we're looking at this, we can have 1, 2, 3, 4. We get a carbon on that. Our second carbon has the group, has the branch. If we go the other way, 1, 2, 3, 4, we have that second carbon has that branch. So in this case, either way is fine. Either of these two options are okay. We end up with 4 carbons with our branch on that second carbon. Like I said, it's a little bit confusing on, where does the carbon chain start and end. Takes a little practice, takes a little trial and error. Just be rigorous, make sure you check everything, see that you're getting the longest that you can. So we have 4 carbons in our chain. And we have our group here. This is going to be a methyl group on carbon 2. And what else? We have all single bonds. Okay, those are the pieces of our molecule name. 4 carbons in the chain means that we have bute as our base. All single bonds means that the ending is ane. So we have some kind of butane. And if we have a methyl group on that second carbon, we can call this 2-methylbutane. And if you chose the other carbon chain that we mentioned, starting at the top right, ending at the bottom right, you should end up with the same name. That is the beauty of our nomenclature rules. If you get it right, you end up with the right name. For our second example, we have some kind of octane. So, okay, oct is going to be 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. I'm going with our efficient skeleton model here, line drawing, representing each carbon as the end of a line or the bend in our line. Okay, on our octane, we have 4-ethyl, 2,3-dimethyl. So our ethyl group, let's draw that one. Our ethyl group is going to be on that fourth carbon. 1, 2, 3, 4. Ethyl means we have 2 carbons. One can be at the corner, one can be at the end. 2,3-dimethyl. This di means that we have 2 of those methyl groups. So dimethyl means that there's a methyl on that second carbon. We have a methyl on that third carbon. And that's it. I think that's what we got. And for clarity here, we can number our carbons. 1, 2, 3, 4, 5, 6, 7, and 8. So these names, they look a little bit like a mess when we first get started on them, but by the end it's just like learning a new language, right? Speaking a different code. 4-ethyl, 2,3-dimethyl octane rolls right off the tongue, and we get this picture in our mind. A note here, when we are writing out our substituents, our groups, we want to tell the number and the name of that group. We want to list these groups, if we have multiple of them, we want to list these groups alphabetically. So ethyl starts with a E, starts with an E. Dimethyl, we're looking at the M. We're looking at the name of the group. The prefix di, we don't count for alphabetizing these groups, although we do include it to show that there are 2 of them. We write our ethyls before our methyls. These groups go in alphabetical order. All right, there we go. Those are our alkanes. If we want to switch gears a little bit, we can upgrade to alkenes and alkynes. Alkenes are also hydrocarbons, but now they contain at least one double bond. Alkenes have sp2 hybridization on our carbons, on at least some of our carbons. And we can start to see what this looks like. The chemical formula, in general, we have twice as many hydrogens as we have carbons. Alkynes have at least one triple bond in our carbon chain. Another type of unsaturated hydrocarbon. We start to have multiple pi bonds as well as our sigma bonds. In order to accommodate our triple bonds, we need sp hybridization. And we can start to see that in some of these molecules. Notably, our geometry for sp hybridization is going to be, 180 degrees. We have straight lines across our triple bonds. Scrolling back here, for our double bonds, we have sp2 hybridization. That means 120 degrees. We have kind of equilateral triangles for our sp2 hybridized carbons. All right, the fun stuff that we're all waiting for. How do we name our alkenes and how do we name our alkynes? Well, we follow the same rules as our alkanes, except we're going to change the ending of our molecule. We can have an ENE ending when we have a double bond. We can have a YNE ending when we have our triple bond. I will try to enunciate here. Alkene, alkyne. These different names will dictate the type of bonds in our molecule. these double bonds or triple bonds, well, we need to have information about where they are. And so we'll indicate the position of that double or triple bond in our molecule name. When we're numbering our carbon chain, we do want to look at all the groups, but the group that has highest priority is that double bond or is that triple bond. So we'll start our chain number so that our double bond or our triple bond is at the lowest number. A note here, when we have double bonds or triple bonds, we cannot spin around those bonds. Those bonds are rigid. Those pi systems make it so those bonds are rigid. For alkenes in particular, we want to be aware of the different isomers. We want to have that in our name as well. If we're looking at this double bond on the first molecule, okay, doesn't matter where we put things. We have one butene. This is 4 carbons with a double bond on the first carbon. But means 4 carbons. Ene means that there's a double bond. The 1 tells us where that double bond is. If we have 2 butene, well, now our double bond is on the second carbon. And actually, we need a little bit more information. We can't rotate around this double bond. We'll look at this in our lab with some modeling kits. We'll see why that's the case. But we can either have a cis version of this molecule or a trans version of this molecule, representing where are the largest groups across that double bond. If those groups are close to each other across the double bond, we call that cis. If those large groups are far away from each other across the double bond, we call that trans. And it takes a fair amount of energy to convert between these cis and trans isomers. They're going to have different properties. They're going to behave differently. They are going to be different. All right. Last little practice problem for this video. We have 2 molecules here. What is the name of the compound down below? And can we draw a certain molecule? Again, let's pause for a moment. Let's see if we can answer these questions. All right, and now that we've had the chance to answer it, let's see if we can make sure we have it right. 1, 2, 3, 4, 5, 6, 7, 8 carbons in the longest chain. So we have some kind of oct, right? Oct is going to be the root name for our molecule. We have a triple bond, which means our ending should be octyne. We want to tell people where that triple bond is. We can either have 1, 2, 3, 4, 5, 6, 7, 8 as our numbering system, or we can do it the opposite way, where we have 1, 2, 3, 4, 5, 6, 7, 8 over at the top right. This is going to be better. We want to have our lowest number at our triple bond. So we can call this 1 octyne. Is that the only thing going on? Well, not exactly. We have this fluorine hanging out, and we have this methyl group hanging out. So we have, what is this, 4 methyl, and we have 4 fluoro. We want to list these groups at the beginning in alphabetical order. So we can call this 4 methyl comes after 4 fluoro, 4-fluoro, 4-methyl, 1-octyne. That's the molecule drawn up here. For our second question, we have hexene, cis-3-hexene. So we have a double bond on the third carbon. Here's 1, 2, 3 carbons. Then we have a double bond out to the fourth carbon. Then we have 5 and 6. 2 more left to draw. This is cis-hexene. So we have two choices. We can either continue our chain going up or going down. For the cis version, we need to do this option, have our groups close to each other. And they're not drawn in, but we do have some hydrogens here on all of these carbon atoms, completing those octets. Cis-3-hexene. I have a few extra things here. Don't need to draw this, don't need to draw this. This looks like a nice molecule. And to be honest, don't need the dots either, but those might be harder to erase. All right. Lastly, we promised to mention some typical reactions for alkenes and alkynes. We have double bonds, we have triple bonds. These are going to be big sources of electrons that are pretty reactive. Pi bonds are going to be weaker bonds, easier to react with, easier to disrupt. And so we can have addition reactions where the electrons within that double bond or within that triple bond can be used to form bonds with incoming molecules. Right? So we can try to take those electrons in that double bond, use it to build bonds between these two different, maybe chlorine atoms. Right? The electrons in that double bond in that pi system get used to turn into these bonds with our chlorines. You could do the same thing with hydrogens or bromines or fluorines, right? Things that want one additional electron to complete their octets. Here's an example where we have a triple bond where the electrons in that triple bond are used, well, all of them are used to do addition reactions with bromine. Again, here we can draw some electron pushing arrows. Oop. Use some of these electrons on that first bromine molecule, some on the second one. These were the electrons in that pi system, but now they're being used to form bonds to other atoms, incoming atoms. All right, thanks for bearing with me. Here we are. If you want some extra practice, we have a few extra practice problems we can put up on the board here. Feel free to try your hand, see if you can name these compounds. Lots of fun. Looking forward to helping you learn the rest of this material in our next videos. Thank you for being here, and I will talk to you soon. Thanks.